This is the first of 4 presentations used to explain the modeling of fuel cell. This is a brief introduction of fuel cells. Fuel cells are electrochemical devices which transform chemical energy into electric energy. In operation, unlike the batteries, the fuel cells are fed continuously with fuel. A fuel cell fed with hydrogen and oxygen, which obtains water and electricity as products. The burning reaction in the internal combustion engine is a fast oxidation, which allows to use only the heat of reaction in order to obtain mechanical energy. Therefore, the electricity production from internal combustion engines is very inefficient. In the figure is shown a scheme of a hydrogen fuel cell with liquid electrolyte. The reaction in hydrogen fuel cells is performed in 2 separate steps. In the left electrode, the anode reaction, the hydrogen molecule is separated in protons and electrons, whereas in the right electrode, the cathode reaction, the oxygen molecule reacts with the protons and the electrons produce water. The electrons generated in the reaction are conducted through external circuit, which allow to use the electric energy. The protons generated in the anode are conducted through the aqueous electrolyte to the cathode, in order to complete the electrochemical reaction. There are some types of fuel cells depending on the fuel used, materials and designs. This assignment is focused on the study on fuel cell, which use pure hydrogen and oxygen as fuel, and it used solid polymeric electrolyte. This type of fuel cells is named PEM fuel cells, proton exchange membrane or polymeric electrolyte membrane. The solid polymeric electrolyte has some advantages compared to liquid electrolyte. High proton conductivity is most important advantage of polymeric materials. The PEM fuel cell is composed by the following fundamental parts: the active layers, the diffusion layers, the terminals of the anode and the cathode, and finally the polymeric membrane that separates them. In addition, fuel cell is composed also of a set of auxiliary components necessary to its operation, such as the seals, the refrigeration system, the humidification system, and the electric control. Let's see some properties of the fundamental parts of the PEM fuel cell. The membrane is a solid polymer electrolyte, usually polytetrafluoroethylene sulfonated, which is placed between the catalytic layers of the anode and the cathode. The free movement of protons in the electrolyte structure from anode to cathode when the electrolyte is well hydrated is the main property of the membrane. In addition, the membrane does not allow the crossover of hydrogen and oxygen. The active layer, also named catalytic layer, is a thin layer located between the membrane and the diffusion layer, where the electrochemical reactions are produced. The active layer has usually 3 components: catalyst, electrolyte liquid, and the physical electrical conductor support, which is usually carbon powder. The ink, result of the mix of these components, is deposited on the surface of the diffusion layer of the anode and the cathode or on the membrane surfaces. Membrane, active layers and diffusion layers are usually named MEA, Membrane Electrode Assembly. In order to optimize the electrochemical reaction, the oxygen and hydrogen molecules should be close to the catalytic particles, as well to electric and proton conductors. The most common catalyst used in the active layers is platinum. The diffusion layers are fabricated using porous material, which allows the diffusion of gases and water to the catalytic layer. High electric conductivity is a very important property of the diffusion layer, which allows the movement of the electron between the collector plates and the catalytic layers. Normally, the diffusion layer is fabricated on carbon, paper or cloth, which are suitable for its conductive properties and corrosion resistance. The main functions of the collector plates are to maintain the structure of the cell, to separate the gases in every single cells of the stack, and to distribute the gases in the MEI properly. The collector plates are one of the most expensive components, as these are usually made in graphite or in matching metals. Some important physical properties of the plates are high electrical and thermal conductivity and gases and liquid water impermeable. The plates are usually designed with channels which allow the adequate distribution of gases and the evacuation of excess water. Modeling and simulation have been widely used in the study of PEM fuel cells. For example, the modeling of gases and liquid water diffusion in the porous media is extensively studied, since the access of the fuel to the catalytic layer in the presence of liquid water is one of the most important topics. Also, the dependence on amount of water in membrane conductivity and the influence of other design parameters on the cell in electrical performance has great interest. Since the most important phenomena of the PEMFC occurs in its cathode, only this part of the cell will be considered. The relevant species in each layer of the cathode are shown in the figure and the table. The physical-chemical phenomena modeled in this assignment are transport of liquid phase and gas phase water in the diffusion layer and active layer, transport of oxygen in the diffusion layer and active layer, electrical conduction in the active layer and the diffusion layer, proton conduction in the membrane and the active layer, and electrochemical reaction in the active layer. In these presentations, some modeling tasks related with the fuel cell modeling will be proposed. The proposed modeling tasks have been arranged in order of increasing complexity. In task 1, the diffusion of a gas in a porous media will be studied. The objective of this task is to model the one-dimensional diffusion of gas in a porous material, with the aim of analyzing the spatial distribution of the gas pressure and the molar flow rate in response to change in the gas pressure applied at one end of the material. This task is an introduction to the control volume technique, which is applied in the other task to model the dependence of physical quantities with respect to the spatial coordinates. In task 2, the diffusion of a binary mixture of gases and a liquid in a porous media will be proposed. The model developed in task 1 is extended to describe the molar balance and the diffusion of oxygen, steam water, and liquid water. As in task 1, it is assumed that the diffusion of the species occurs only in one direction and the porous medium is divided into control volumes along that axis. The balance of steam water and liquid water due to the evaporation and condensation processes are taken into account. In task 3, the electric conduction and electrochemical reaction and complete model of the fuel cell are proposed. The objective is twofold. Firstly, to model the electron and proton conduction in the membrane, the catalyst layer, and the diffusion layer of the cathode. Secondly, to model the electrochemical reaction that takes place in the catalytic layer. Combining this model with the models developed in the previous tasks, the complete model of the PEM fuel cell is obtained. Finally, the model of the electrical circuit to polarize the PEMFC model is developed. In order to increase the knowledge of fuel cell An additional bibliography is recommended.